This is 0625, Physics Major, paper 62, 2024. So in these papers, he will explain to you what he wants to do with the set of experiments that he's going to conduct, and he will tell you what he wants to do with them. So he mentions what he wants to do. He wants to measure the spring constant of a spring by two different methods. So the spring will stay the same, but he's going to try it with two different methods. And we understand that the spring constant is basically force equals to Ke, or sometimes you like to call this as Kx. This is the spring constant we're talking about. So this generally will be K equals force divided by extension by a letter E, or force divided by extension X. In some syllabuses, they use E, in some they use X. Whatever you choose to go with, it's fine. The student attaches a spring to the clamp shown, okay, fine. And then it pulls down the mass and then releases it. So when you pull it down and then you release it, we're expecting it to oscillate between two positions, going up and down. So the mass oscillates as he mentions. This was our prediction, and this is what he was trying to find the time for. Time t for 20 oscillations is given to you as 17.76. Now, the period t of oscillation is taken for one oscillation. Calculate the period t. So now small t represents oscillation for 20 oscillations, and capital T will be for 1. So write down 17.76 seconds over here, and then divide this on the calculator to write down what a single oscillation would look like. So that would be 0.888, or could be 0.89. So again, the idea is two significant figures. Moving on, in part B, suggests how the procedure can be improved to increase the accuracy of the results. Measure time for more than 20 oscillations. So that is a general idea. And the reason behind taking more oscillations is that it reduces the human reaction error. In part C, he says calculate K1 by this method, so it's 19.1 divided by T square. Now, this will definitely be 19.7 divided by 0.89 whole square, which will lead towards an answer of 24.9998 something probably, and then this will come down to 25 newtons per meter. Since we are taking two significant figures, we can leave this as 25. If we had taken 0.888 full, then this is three significant figures, this is three significant figures, we could have written down as 25.0. But for now, since the smallest value I'm taking is two significant figures, I can round this down to two significant figures. I will do that. The student measures, now this is the start of method number 2. Student measures the length L, and it's measuring to 0.1 centimeter, which means that when you place your ruler on top of this to take measurements, and I would advise you to take a transparent ruler to do that, just superimpose the image of the ruler onto this one, and then take those measurements, and always start from a value that is not 0. So, for example, if you have a ruler, I would advise you to start from a value that is other than 0. So if you're starting from 0, this is not entirely a good practice in physics, at least. So what I would be assuming, or what I would be expecting from you, is to start from a value that is other than 0. So you could be starting from, let's say, 3. And this goes up to, let's say, 13 point something. And then take the difference of 13 point this and 3, and then find the length or the value that you're looking for length. Avoid starting from 0. Again, for the case of 0 error, probably. Okay, so it's 1/4 of the full times, which means that it has been divided by 1/4, or all the measurements have been divided by 4 to actually show this on the paper for you guys. It says measure the length L, the dotted lines, and once we've done that, we can see on your paper. Again, if you're doing this at home, you will realize that due to different magnifications of the people who print this exam, the values will come out a bit different. But don't worry, in your examination, this was already been known by the examiner, or at least the teacher who's taking your classes. They would know this, so they would know that this is a bit smaller or a bit larger than the actual paper. So no need to worry about that. So this would be 5.5 again. I'm just trying to copy the marking scheme here. And over here, this will be this is supposed to be 5.6. So 5.6 multiplied by 4, because this will be the actual stretch length, which is by 1/4 scale. So this will come out as 22.4 centimeters, or 22.4. We are not doing the significant figure rule here because he mentions that we are measuring up to 0.1 centimeters. So I have to add this one decimal place for the sake of accuracy. And you will see this in this table as well. He is following that 0.1 centimeter rule to follow through this table. Anyways, now he mentions that the student removes this mass and then records the value of L in table 1.2, and we've done that already. Okay. Now plot the graph of length in centimeters versus mass in grams. Now, you will notice in other papers that this graphical question, is generally for 4 marks. The reason this is now for 3 marks is because he's already mentioned the axis labels, which actually carried 1 mark previously. Now, since this has already been done for you, it will not be given as a credit. But anyways, let's figure out what spaces do we have. And what I generally, again, advise to the students is always write down these small additions to the table that you're drawing the graph of. So mass is going to be on x-axis and length is on y-axis. So whenever I go back to the table, I don't have to figure out that whether I'm looking at x-axis or y-axis. This is already done for me because I've added these details. Again, you could be doing it with a different method. It's completely fine what you choose to do it with. Okay, so the scale I'm going to choose is going to be 100, 200, 300, 400, 5, and then 600. And on the y-axis, I am going for a scale of 5, so 5.0, then 10.0, 15.0, and then 20.0, and then 25.0, and then 30.0. So again, I'm drawing the expected locations of these graphs. I'm not going to be entirely accurate with them. I'm just drawing them in a single go wherever I've done on my paper. So there's going to be a coordinate somewhere around this area, 100 and some value. Then with 200 and probably 10 something. And then 300 with something below 15. And then 400 with expected value around 18 or 19. Then 500 goes a bit more than 20, somewhere around here. Yeah. Then I will draw a straight line, and then please make sure that this is the line of best fit. You don't have to force this through the origin. Sometimes we do, sometimes we can't do that, because in this case it won't be possible. Why? Because L is actually the total length of the spring. So it's quite obvious that it wouldn't pass from the origin. If it had been extension, then definitely it would be passing from them, but it's not extension. It will be passing from somewhere along this line. So that means that all the load has been removed, and what's the actual length of the spring or unstretched spring at this moment. But anyways, so draw the line of best fit. It should be passing from all the points. The first priority, second priority is equal number of points above and below the line, and the third priority is that once you've managed to equalize the points above and below the line, make sure that their distance is exactly the same as well from above and below the line. So I have missed out this point, but be advised, it can be for your graph as well. If most of the points are on the line, then one point being below the line or above the line is acceptable. No need to worry about that. So the most common part will be to find the gradient, and as I've mentioned before, always take the largest possible line that you can. So pick a coordinate from this region and pick a coordinate from this region. This actually justifies their requirement and condition that more than 50% of the length should be taken for a gradient. And please avoid the coordinates that you've already taken from the graph. They are not going to be representation of the line itself, because some coordinates are going to be below, some are above the best fit line. They are not representing the line itself. We are looking for the gradient of the line, not the coordinates. So please don't take the coordinates themselves that are from the table. So choose new coordinates. For example, add a circle that these are the coordinates that you're taking up. I wouldn't put a cross over here. I would put a circle. to be different from the crosses that I've put for the coordinates. And then I would draw a dotted line with the help of a ruler to show the examiner that these are the coordinates that I've taken, and this is the triangle of gradient that I will be choosing. So then the next idea would be to show the coordinates that you've taken. In my case, I was taking 50, 4, and 540, 24. And then simply show to the examiner that the formula that you're using, so this will be 24 minus 4 divided by 540 minus 50, and then show that gradient G is going to be equal to 0.0408, which will then be written down as 0.0408. So then he says use the equation to find this one, and then again there is no problem in simply substituting the values. K2 equals to 1 divided by 0.0408. The value comes out as 24.5 Newton per meters. Let's write it down as 24.5. Moving on, he says that compared to this is going to be a repeated question. This is going to be a repeated part, so please be careful about this. He says that verify whether they are within the limits of experimental accuracy. And I've explained this part before. You can do this by any means that you like to do this. So first and foremost, write down the value of K1 or the values that you're trying to compare. So let's say this is K2, which is going to be 24.5. Now, on the looks of it, I can very well say that they are very close to each other, but there is a criteria for how close they can be in physics that they will be accepted as being close to each other. That can be tricky for a common man perception. But we will back this up by a mathematical allowance, or you can say we have a license to do that. So the license is that they should be within 10% of each other. So choose anyone, either 25 or 24.5. For the sake of example, let's say if I choose I'm choosing 25 because it's going to be easy to calculate the maths for this. So 10% of this value of 25 becomes it's going to become 2.5. So it becomes 2.5. So add 2.5 and subtract 2.5 from the same value. So this will give you the range of values. So our range from 25 down below becomes 22.5, and in the upper side it becomes 27.5. Now the other value will be tested on this range. Does this come in this range, or will it belong within this range? And yes, it does. So if your answer is yes, it belongs to the range, then yes, K2, I will say that K2 and K1 are similar, or you can say they are equal within the 10% experimental accuracy, or within 10% of each other. So I will accept that both methods have produced the same results, and the spring constant of this experiment will be 25. Question number 2, electricity-based question. He said investigating the resistance. So he wants to measure the resistance of a diode using the circuit below. Okay, fine. So he closes the switch, measures a bunch of values of voltage and current, voltmeter connected across the diode, ammeter measures the value of current in the circuit, series circuit, and we have to write down these values in this table. So if we go back for the voltmeter, this is going to be 0.84, and this seems to be 0.36. Now, these are 10 divisions, so this should be 0.01, 2, 3, 4, 5, 6, 7, 9, 1. Yep. So every division or big division is probably 0.1. So 1, 2, 3, 4, 5, 6. Yes. And then those 0.01 are being divided into further 5 divisions. So 0.01 divided by 5 would give you around, I think, 0.002 probably. Let's just verify this. So 0.01 divided by 5 is, yes, 0.002. And from that moment onwards, you just have to count the values. But I think it should be 0.02. Yeah, it will be 0.02. But anyways, So the final value will come out as 0.36, and this will be 0.84. Again, simple counting. So this will be 0.84. This will be 0.36. And then he's going to ask you to use the value of resistance or the formula to find the value or fill in the table. So I can see that one of the values filled for me. So I'm going to follow the same format. So this will be 2.333, but I'm only putting down 2.3. Similar thing for the second column as well. This will be 3.1. And then again, I'm going to follow the trend in the column. So these ones are being rounded off to probably 2 decimal places. So this will come out as 0.18. Yeah. So he does mention that record them to appropriate number of significant figures, but we have filled the table with the calculations based on the trend in the column. So we can say it's 2 significant figures throughout. Yeah. Student then connects a 3 ohm resistor and then 1 ohm resistor and so on and so forth. Repeats experiment procedures in A. Repeats experiment in this case. And then a table is complete. Complete the values by adding missing values. We've done that already. As a student, I think, are the units there? So sometimes he will miss out these units and add that point as an extra mark question. He says that the resistance between X and Y, let's just zoom in. As the resistance between X and Y is increased, the current in the circuit changes. Now he is not mentioning how it changes. He's going to expect this from you. Use your table in 2.1, very important to refer to the values to state the relationship between the current in the circuit and the potential difference across the diode. So we are supposed to explore between current and potential difference for the first part. So what's going to happen? So what's happening to the potential difference? It is decreasing slightly. And the current is also decreasing. So, or as the current decreases, the voltage is also decreasing, but not to a high extent. So you can argue that if when the current decreases, the voltage remains fairly constant, or you could have said it decreases slightly. Both answers would have been acceptable. Because if a student says that it remains fairly constant or it remains constant, it could be because of the error in the ammeter, because it's a digital one. It's quite possible because of that. But again, both answers are acceptable in this case. The resistance R of the diode. So between the current and the resistance, as the current is decreasing, the resistance appears to be increasing. So we will write down that as the current increases, the resistance decreases probably. The resistance also increases. So this will be as the current decreases, the resistance increases. Yeah. So a student attempts to set up the figure 2.1. Okay, fine. The student finds that the ammeter does not give a reading when the circuit is complete. The ammeter is not broken. This is again a common question in terms of an element involving a diode. So he wants you to think, why is that the case? Why the current is not flowing, or why the ammeter is not giving a reading? And that's purely because either the diode is flipped or either the power supply is flipped. What does that mean? Is that, for example, in the same question, let's go back to 2.1. Yeah. So this positive means that the current is going to flow from this terminal. Again, we're talking about the conventional current. And the simplest way of this, of what I've told my students, is to remember that if the current direction is similar to the direction of the diode's arrow, then the current will be allowed to flow. If it's the other way around, the diode will not allow the flow of current. So either by mistake, somebody has connected the positive terminal to this side and negative terminal to this side, which means that now if this is the positive and this is the negative terminal, and the current is coming this way, which will of course make the diode reverse biased, and the diode will not allow the flow of current. And if the ammeter is not broken, definitely there will still be no current in the circuit. Or what this student might have done is that he has not disturbed the battery, is not flipped the terminals of the battery. What he has done by mistake is connect the diode in reverse. Now, if the diode is connected in reverse, same thing will happen. If the current is going to try to come from this side, the arrow of the current, conventional current, and the arrow of the diode are in exact opposition to each other, which means that the current will not flow, which is again going to show up as no current on the ammeter. The method of the arrows that I've shown you is not a scientific method, but it's a method to remember things quickly. There is a lot going on inside the diode which enable this function that the diode actually performs, which has to do with potentials, which has to do with bridge, which has to do with positive and negative charges. So it's a complete separate physics. But anyways, we can remember by the logic of the arrow how to deal with it out to keep things simple. So that's what we've said over here, that these could be the problems. So name a single device that can be used to control the current, and that the simplest one is a variable resistor. And the electrical symbol for that would be this one. This actually entails all the variable resistors in it. It could be a thermistor, could be a LDR, could be a rheostat, could be a potential divider. If he has mentioned, or if he had mentioned, draw a specific one, then of course we will draw a specific one. But this is the general symbol for variable resistor for all of the components that are going to fall under the same umbrella. Question number 3 is a bit tricky. Now, in this question, I would advise you to do as the examiner says. Don't try to make your own light rays. Don't try to make your own physics. Don't try to do anything. Just quietly follow the examiner, what he wants you to do, and you will be fine. So he says he wants to find the refractive index. This is our target. And yeah, there's a ray sheet and there are blocks. I'm going to zoom out a bit so that we can see the block completely. Okay, so there are some labels A, E, B, C, D, and F. And there are some pins placed on the outer side over here. Now, this question has to be done with a lot of straight lines. Unfortunately, can't do that over here, but I will try to be as accurate as possible. What I'm trying to teach you here is that follow the instructions of the examiner. Don't think too much about this. If you start thinking about this question too much, you will lose time. So let's follow the instructions. He says on figure 3.1, draw a normal at point E. First instruction, close your eyes and just follow this one and just follow the instructions. Not with closed eyes, but of course with open eyes, but don't think too much. So I draw a normal here. Now he might say that extend the normal above AB and below CD. So what I'm going to do is extend this above AB and below CD. This is what he means by this statement. And you will find that this is what he does in ray box questions generally, if you practice them long enough. Label the upper end as letter N. So I will label this as N, and the lower end of the normal line with letter M. So I will add M over here, where the normal crosses the side CD of the block with the letter G. So wherever it crosses it, this will be the G. Now he says measure the angle theta between FE and EN. So you might be confused by this. FE-EN, what does that mean? So he's actually trying to measure this angle, this one. So FE and then E to N is actually the angle of incidence, what he's trying to say. But since he does not want to use the proper terminology in this paper, because he's not required to do that, he's taking a longer route to maybe probably confuse you even more. So when you measure this angle with a D or a protractor, your answers will vary, but generally around 60 degrees. Then the student positions the illuminated slit on the trace line. Let me zoom in. So that the ray line passes along the line FE towards E. He marks the label with 2 cross points along the line CD. When it leaves it, removes the transparent block. On the figure 3.1, extend the line FE until it reaches the right-hand edge of the trace sheet. So where's the line FE? So yep. So you will place your ruler like this and extend the line as far as you can until it reaches the end of the sheet. Okay, so somewhere along this point. Let's extend it. So we extend the line with a ruler and end it here because that's what he mentioned. We are done with the first point. So label the end of this line as Z. So we simply write down the letter Z here, somewhere along this line. Yep. And then he says, draw a straight line through the 2 crosses that meet CD. So let's do that. So CD, again, straight line passing through these lines. Label the point where the line meets CD with the letter H. So we go here and we label this as H. Then we have labeled the other end of the line with the letter J. So this will be J. We've done the labels, and then he says draw a straight line from E to H. This is why labeling was important. So please follow along. So E to H would be this line coming from this point up to this point. And now it makes a bit more sense to the common student who might have done these questions as ray box questions in their classrooms as experiments for the refractive index calculation. Now it's taking a bit more shape. Again, do all of this diagram with a ruler. It can't be done with the freehand. Now he mentions that measure the length L of EH. So where's EH? So you will be measuring the length of this line, whatever your length may come out as, take it as it is, and just put it here. So I'm just writing down the answers from the marking scheme, which will be 7.5 centimeters, and perpendicular distance D between HJ and FZ. So where's HJ? So this is HJ, and this is FZ. Perpendicular distance. So he's looking for this. Okay. Or probably this. Right? So this will be the perpendicular distance. Right? So measure this distance perpendicular so that it makes an angle of 90 degrees. And this will come out as 3.0. Yeah. This will come out as around 3 centimeters. So 3.0. Then he wants you to calculate D by L. Again, dividing this with this. So mention the 3.0 divided by 7.5 will give you an answer of 0.4. Yeah, 0.4. The measurement of a quantity is reproducible if a similar result is obtained when the measurement is repeated by the different method or under different conditions. Suggest how the student can adapt this experiment to check if the value of D by L is reproducible. So simply just repeat the experiment with an angle of incidence greater from the side CD. For example, just twist the block, and you're introducing the light ray from this side. Let's do it from this side with the same angle of incidence as 60 degrees, and it should produce the same results. Again, so just one source of inaccuracy. There are many sources, but we're going to write down, I'm going to mention all of them. You can write down only one. So it's difficult to get a thin ray. What do we mean by a thin ray? So these are two examples. Now the left one represents a thin ray, which is a bit difficult. And you have to do the experiment in a very dark room, which sometimes is not possible because of a lot of students are probably in the same lab. It's not safe. You can trip, or you can maybe, again, maybe not arrange that for 30 or 40 students at the same time. The right image is actually a thicker ray. It's not as thin as the left one. So this is what he means by that. It's difficult to set up a thin ray and still be able to see it in the dark room. Difficult to place a process, it definitely is. So when the light rays are passing through, you have to place thumb pins or common pins on those places while you're looking at them from this side, so that they are exactly in the same line of sight as each other. It's difficult. And also one of the procedures of improved accuracy is that this distance between the pins should be greater than 5 centimeters. And then difficult to judge the center of the ray, because if the ray is thick, let's say if the ray is thick like this, where do you put the pin? Do you put it here? Or do you put it here? Where do you put it? So you have to make a judgment call, because if you put the ray, let's say if you put the pin somewhere here, then the measurement of angles will be up to this point. If you put a ray on this edge of the thickness, then it will be up to this point. So the angles are going to differ a lot, which is why this adds inaccuracy in the whole system, in the whole procedure. Measure the length L of GH. So let's go back. Where is GH? This is GH. So from this point to this point, when you measure these on your paper, this will come out as probably 4.3. Use a value of L, and from now be careful. This is small l and this is capital L. This is the capital L and this is the small l. So you'll have to go back and find quickly where the small l is. That is 7.5. So then he said that refractive index comes out as L, which is the small one, which was the smaller is 7.5. So 0.866 multiplied by 7.5 divided by large L, which is 4.3. The refractive index comes out as 1.510. So this will be 1.5. Generally, it is around 1.5. Question number 4, he says, a student sets up the flexible track in the edge of the bench. The student investigates the metal ball as it rolls around from the track. The metal ball travels horizontal distance d, which is mentioned on the image, through the air and lands in the tray of sand placed on the floor. Okay. Plan an experiment to investigate how one variable affects the size of this distance, which means, or which could be, are you going to change the mass of the ball and then see how far it lands? Or are you going to change the height of release of the ball? Are you releasing it from this point, from this point, from this point, from this point, and from this point, and see how far it goes or lands? So there are two possible positions or two possible choices you can attempt the questions with. I'm going with the different height. You could go with different masses, but be advised that if you go with different mass, then, for example, if you're choosing 100 grams, 500 grams, 300 grams, so on and so forth, make sure that the point of release is exactly the same so that every ball has same gravitational potential energy, or at least in terms of height, they have the same gravitational potential energy as a comparison amongst each other. So that will be a constant for that case, but since I'm taking height, I'm taking mass of the ball to be constant and trying to investigate if I increase the height, does it go beyond a certain point, or is there a limit to this? So what do we have is flexible track, like a cardboard. We have clamp, Bose clamp, and stand and support the track. Selection of metal balls, yes. Okay, so in your plan, now again, as my previous explanations, if you just simply answer these questions, you are generally set for the whole paper. Apart from them, just add one safety precaution, safety measure, or just a little bit of tiny detail that will help the examiner understand that you actually have thought really hard about this. Okay, so state one variable you have chosen to investigate. What I have done is mass of the ball is independent variable and is selected to be investigated. Or you can choose mass of the ball to be kept constant and the point of release is also kept constant. For example, again, I've explained this earlier, how you can do this. If you're changing mass, the point of release should be the same. If you're changing the height, the mass of the ball should be constant. And that is how you're going to crisscross through this. To measure the mass, you can use beam balancing to measure the mass, but since we are not doing that, I will be using a ruler with a Bose clamp to measure the D. So what I would do is attach a Bose clamp over here and attach a meter rule at this point. So I can probably find the point of location with a set square where the ball is going to be released from. Then ball is released from same point marked on the card, again for different masses questions. And again, I could do with changing the distance or the height. So in this one, we have, let's say in this part, we are changing the mass. Another one could have been, or the option that I'm going to choose, or I would have gone with, would be the height of, or the point of release. It is also going to be in centimeters. So that could have been, let's say 5, 10, 15, so on and so forth. And please be advised in terms of concept that the height that you're measuring will be from this point onwards, the vertical height. Okay, don't just read this ruler. You have to measure from the basement, from the base of the bench. And then, for example, we have mass of 50 grams, 100 grams, and 150 grams. I would advise you to repeat the experiment for the same mass being released from the same point at least twice. So you get a reading first time, you get a reading the second time, and then you add them together, divided by 2 to get the average value of the distance. This is that added detail that the examiner is expecting that you would add in light of improving the accuracy of the experiment. Don't just say repeat an average. Always tell the examiner, what are you repeating? So I'm repeating the experiment for the same mass of the ball, and then I take the average of the value of D climbed, or you can say traveled by the object. And then taking 6 readings and 5 readings. So, yeah. And then taking 6 readings for different masses and populate the table, of course. Yeah. And then draw a graph by taking, and again, mention what are you taking on one axis and the other on the distance on the y-axis. As the mass increases, the distance also increases. This is our conclusion, our prediction for the results. You don't need to add values in the table. I'm just mentioning these values so that you can visualize what we're supposed to do. And this is how you answer this question. And notice I didn't have to use both pages. Your answers can be very precise, very straightforward, and definitely they can fit into one single page. You just really have to be careful about following these points. Yeah. So you can see that a table was mentioned with headings. We mentioned what I'm trying to keep constant. I mentioned how to do the experiment, which means that I'm going to tell him or tell the examiner that I'm going to release the ball and expect to measure the value of D. And any additional apparatuses, we mentioned, let's say set square, or we mentioned beam balance, which was not mentioned for a question with different masses. Anything that you might need that's not mentioned in the question already. And you are not required to enter any readings. That's what I was trying to tell you, that you don't have to add values. You just have to show the examiner how to take values. For example, if you go back, you can take inspiration from what examiner already does. This is how the examiner wants you to do it. But again, we just add labels and headings, but we don't write down any values in them. Okay. And explain how to use the readings to reach a conclusion. We have used the readings to reach this conclusion that as the mass is increasing, or if you're choosing let's say, choosing to do with the graph, you can say that it's a straight line, which means that if mass is increasing, the value of D is also increasing. That's evident from the graph. Okay, and if you choose to show what the graph should look like, then be advised, you just only have to mention what the axis would look like. You don't have to populate or don't have to add coordinates on the graph or show a trend line. You don't have to do that. You just show what he needs to fill in. That is all.